Ready for video number 6 for our solids and solubility chapter? This is going to be actually this particular video, this concept I'm going to break into two separate videos. First one will be qualitative, second one will be more quantitative. But we want to look at, hey, we've studied solubilities of solids now. Can we manipulate that in a laboratory scenario or an industrial setting? So can we increase the solubility of a solid? We looked at how to decrease it by adding common ions. So we already covered the common ion effect, right? You add the common ions, shifts back to the left, right? Making more solid, right? So it decreases the solubility. But what if we want to dissolve more solid? We want to shift it to the right. How are we going to do that? We've already looked at 3 different ways. So let's review them all. And I'll do some math for the third one. So numbers 1 and 2 I'll do in this video. This will be a quick and painless one, good little review one. So I recommend, if you want to completely comprehend what's going on here, review the video on the salt effect and activities. That's an independent video, not in any playlist or separate, or it's in its own category, right? It transcends the different chapters. Then I would review the chapter on complex ions for us. That's chapter 24, and how to impact solids by adding ligands, right? So you could actually dissolve a precipitate in favor of forming a complex ion, possibly. So we'll cover the salt effect. So I'll just review these 3 and then we'll do each one separately. So the salt effect can shift an equilibrium to the right, causing more solid to dissolve. Because if you decrease the ion concentrations on the right-hand side, Le Chatelier's principle says the solid's going to dissolve more to replenish those ions. It wants to keep those ions at a constant concentration so that KSP, the constant, stays constant. Adding ligands, right? So if we add ligands in a high enough concentration, we said something like 4 molar, 5, 6 molar or higher, we could pull those ions out of the solid because these ions go, I'd rather dance with you, complex ion person, rather than with the precipitate I'm currently with. So it's like at my junior prom when my date decided to dance with someone else. But anyway, that was a different story. I was the precipitate. He was the complex ion formation. Whatever. High school. All right. So if it's possible, all right, we can form a complex ion in favor of the precipitate, and the precipitate dissolves. Or at least it may not dissolve completely, but its solubility would increase. Or alter the acidity. That's a real common way. If that precipitate has a cation or anion in it that has acidic or basic behavior, right? So if it has acidic behavior, I could add base to it, right? Neutralize it out. So the driving force would be the formation of water. If it has a basic ion, like OH minus, carbonate, something like that, well, we could add a little bit of acid, adjust the pH a little bit, and cause that solid to dissolve a little more or completely. We'll do some mathematics with that one. So let's cover 1 and 2. I'm going to pause this, erase the board. Let's just review the salt effect, review the complex ion stuff, and then we'll get into some juicy stuff with the pH. All right. I took a little time to look for kind of the nastiest, hardest, weirdest looking solid I could find on the KSP table, just to have some fun. So I found this really nasty one. Where is it? Iron 3 ferrocyanide. Whoa, that'll spin your head for a little bit. So it's a solid containing a complex ion. So technically it's a coordination compound. So iron 3 ferrocyanide. And the ferrocyanide is kind of a nickname. There's, I think it's ferro and ferro or something like that. But so here's the compound. It's got 2 irons in it. Isn't that weird, huh? So the iron is a +3. And then the complex ion, and we have 4 of them. So you get the 4 positive 3 ions when the solid's in equilibrium with its solution. And then we're going to get 3 of these complex ions. So that would be like a hexacyanoferrate 2 ion. Check me on that one. I need somebody to check me on that. But they just call it ferrocyanide because it's a nice little nickname for it. It's pretty common. Quite beautiful colors, by the way. So here's an equilibrium from some really ugly looking solid. Not important, right? It's a big ugly dog that's barking but doesn't bite. we want to go, how can I increase the solubility? How can I shift this to the right? All right. Definitely, if I added iron or that complex ion, it would go the wrong way, right? It would decrease the solubility. So we can't add a common ion to do that. But remember the salt effect. If you add an inert salt with ions that are not part of the equilibrium, they're going to get in the way of these ions recombining, right? They're going to inhibit the process going to the left-hand side. So it effectively reduces these. Remember, that's where we get activities, the effective concentration. So the presence of these ions lowers or masks these concentrations, effectively dropping them, and so the solid would dissolve more to try to bring them back up to keep the K value constant. So let's say we add an inert salt. Add an inert salt. Like, let's say, now we don't want to add something that could react with those. That would really increase the solubility. Okay? Something that would form another complex ion or something. So let's do like potassium nitrate. All right, potassium doesn't do diddly squat. Nitrate never does. Doesn't form precipitates, complex ions, nothing like that. But let's look over here. I'll do it the potassium ions in green. The potassium ions, if we add these to this, originally was pure water, they're going to migrate over to the complex ion because the positive charge of the potassiums, right? So potassium is a +1, and the nitrate is a -1. So we're not adding common ions. We're not adding ions that react with any of the species. So the potassium ions are going to kind of lurk around. They're not reacting with it, but they're going to lurk around and form kind of this shell around that ferrocyanide ion, making it harder for it to combine and reform the solid, right? So it's effectively masking it, and it's dropping the concentration. The nitrate ions, on the other hand, they're repelled by that, but they're attracted to that iron 3. So there's nitrate. They're not going to precipitate. It's not that attractive. But you're going to get these nitrates floating around, hovering around this iron 3. And that's a really highly charged ion. They're pretty, remember, the higher the charge, the more intense this effect is. So you get these inert salt ions floating around, and that will effectively reduce the concentration of those ions, right? So effectively, the concentration of the iron 3 ion and the concentration of the ferrocyanide ion, boy, I picked a tough one, didn't I? Go down. And what happens when you decrease the concentration? So says Le Chatelier's principle. That's going to shift right. So that shifts the equation right. Shifts equilibrium right. And the solubility increases. So nothing new here. This is a review, so go back and if you're rusty on this, if you're a little rusty-dusty, got to blow some dust out of your brain there, go back and watch that video on the salt effect and activities. That's why it's better to use activities, right, or effective molarities than regular molarities. All right, so that's that. Let's look at let's do a little review of complex ion formation, and then in a separate video, we'll look at the pH effect, right, affecting solid solubilities if they have acidic or basic ions. All right, did you review your videos on the complex ion stuff and the complex ions affecting solubility of solids? So this is covered in chapter 18 for us on solids and in chapter 24 for us on complex ions because they overlap each other. It's a pretty common thing. It's kind of neat. And if you don't learn about complex ions, this can happen in lab. You'll have a solid just disappear, forming this beautifully deep, rich colored solution. You're like, what happened? If you don't know what a complex ion is, you're like, I don't know. Right? You're like, well, that's why complex ions, are good to learn about because it forms an amazing, amazing branch of chemistry. So you got to open that ugly door and step through to get into that world, and then you start to go, oh, throughout your life you go, yeah, there's that complex ion thing, right? Although that last one I did was pretty ugly. So here's a typical problem. Show how, we're not going to do any major quantitative stuff here. Show how adding a 6 molar solution of ammonia, notice I didn't give you the formula, to a saturated solution of silver chloride solid, right? So you got that solid, you can see the solid in a container and the solution above it, and you can hopefully mentally see the silver and chloride ions in solution in equilibrium with that solid, right? Where the rate of dissolving, the rate of formation are equal. How will adding that ammonia increase its solubility? Right? Doesn't mean it's going to completely dissolve. It's possible it can completely dissolve. We'd have to run this in lab. We'd have to test specific concentrations to do it. So let's just look at it qualitatively, see how that affects K values and whatnot. So we're going to be adding equations together like we did in chapter 24. So let's set up equations. Let's start with the topic of interest in this is the solid. So let's do equation 1 and set up the solid equilibrium. Right? So let's call this equation 1. So we're going to have the silver chloride solid, and that's going to be in equilibrium. It's just minding its own business, right? I'm just a solid sitting here by myself doing nothing. And then we jack some ammonia in there. The solid goes, what are you doing? You've disrupted me. Right? So that's pretty nice. And we could look up this K value. This would be KSP, correct? So this would be KSP. We good? And we can look that up on a table. We don't need to right now. What happens is we add ammonia. We're adding ammonia. So let's take a look. We're adding a species. So we have to go, and that's not an ionic species, so we don't have to worry about cations and anions. We only have to worry about the ammonia. If we add ammonia, can it react with either of these to form a precipitate, acid-base neutralization reaction, or form a complex ion? You have to think about the possible combinations. So ammonia, if you remember from your coordination table, is a ligand. That nitrogen has a lone pair. Ligand. All right, so there's my ammonia. So and we know that's gonna only go with a metal, so that wouldn't react with the chloride. Okay, so hey, look at that. There's silver right there. So that can form a complex ion with a coordination number of 2. So that can pick up 2 of those ammonias if it's in high enough concentration. Oh, which it is. Yay, hint, hint, giant flag right there on an exam, 6 molar. All right, so that's my way of saying, hello, I want you to form a complex ion. So that ammonia can react with this silver. So let's bring that silver down to equation 2. And that silver ion is susceptible to attack by the ammonia. So how do we know it's 2? We looked up the coordination number on that table. So the ammonia is a monodentate ligand. 1-tooth vampire, so one here on either side of that, forming a linear species. Right? So our complex ion will be the silver with the 2 ammonias. Let's see, ammonia's neutral, silver's a +1, so the overall complex should be a +1. So diamine silver 1 ion, because it's a cation, so we don't change the name, we just call it silver. So diamine silver 1 ion, I think. Remember the nomenclature video? And so that K value, that is the formation. It's not backwards, right? The definition of Ks is formation of it. So K2 will be the Kf value. And this is a solid dissolving, so that's the definition of a KSP equation. It's not backwards, so we don't have to inverse anything. Now, when we add these together, remember the ion that's common between them, the silver, must go bye-bye. Right? So we're trying to get rid of. So if I add these together, I'll get 1 silver on the left and 1 on the right. So they're going to go. I don't have to multiply either of these. I don't have to manipulate them by multiplying them by 2 or 3. I don't have to reverse them, so I don't have to inverse the K value. Remember all that fun stuff? So I don't have to square that. I don't have to cube it. I don't have to do anything. When I add these together, I'm just going to do K1 times K2. I'm going to take a KSP of that solid times the KF of this complex ion formation. See who wins. It's just a straight head-on battle. Is the KSP more favorable or the KF more favorable? And that silver ion is going to either go, I want to stay with the solid, which is what I was hoping for my junior prom. But no, what happened is, no, I would rather be with this person here and form this complex ion. Now, you never know. Depends on where that silver ion wants to be. Horrible analogy, but I'm still suffering psychological ramifications for that over 30 years ago. All right, here we go. Let's add these together. Wow. So here's our overall equation. We did this a lot in chapter 15, didn't we? We're going to have the silver chloride solid. The silver ions go bye-bye. So we're effectively adding the two ammonias. Nothing left on the left-hand side. So that plus that goes away. That goes away. We're going to get a chloride over here plus the complex ion. I'm running out of space, gang. And voila. I'll squish my AQ in there. Squishy 0.2 font. We'll have to, obviously, I'll have to calculate the overall K value on the next board. But you can go ahead and do that. Just look up the KSP value for silver chloride. Look up the KF value for the diamine silver 1 ion. Multiply them together and see what your K value is. If that K value is way greater than 1, that's going to dramatically drive to the right-hand side. If it's greater than 10 to 10, it pretty much goes to completion. If it's less than 1, it means it's going to be a little more reactant dominant. If it's around 10 to the minus 10, that means this probably won't go at all. But if it's somewhere in between there, right, that will dissolve a little more. It'll increase its solubility. Maybe not completely, but it definitely will increase it. So calculate the overall K for me. I'll be right back. All right, gang, if you do your math, hopefully you get what I get, unless I boofed it. So it's straight up. You add two equations together, Hess's law, right? Rules of equilibrium. You multiply the K values. And again, we didn't have to manipulate them, inverse them, raise them to the power 2, nothing like that. I looked up the KSP value for silver chloride. So if you look in different KSP tables may give you slightly different values. So silver's here. Lots of silvers. There's silver chloride. Right there, and there's your AgCl. I get 1.8 times 10 to the minus 10. 1.8 times 10 to the minus 10. That's where I get the silver chloride KSP. Now I want to look up the KF, and that was for the diamine silver 1 ion. So you're looking for the silver. Here's silver, and there's the complex ion of interest. See the 1.6 times 10 to the 7. Right? These are usually huge. They're very favorable if you have high concentration of ligand. 1.6 times 10 to the 7. That's where that number comes from. Two significant digits. Boom, I get 2.880 times 10 to the minus 3. Good to 2 sig figs. So that rounds up to 2.9 times 10 to the minus 3. Now again, that's not bigger than 1, so I wouldn't say this is incredibly product favorable. Right? It's actually a little more favorable to be the silver chloride on the left than the complex ion on the right, but not by much. Okay, that's nowhere near 10 to the minus 10 or anything like that. So this will definitely cause some of that silver to leave the silver chloride and go into the complex ion. So the solubility of that silver chloride would increase. Now, how much numerically? We didn't do a quantitative problem like that, which we could. You can read that in your textbooks and things like that. But we would need specific concentrations and other information to be able to do it. But qualitatively, you could see, yeah, that would increase its solubility, right? So we covered inert salts, right? From the salt effect, increasing solubility, shifting equilibrium to the right, adding a ligand to react with the metal ion to form a complex ion. That'll shift it to the right. And then the next video, we're going to look at adding acid or base to neutralize an anion or cation in that solid to create water, right? And that will effectively shift that baby. It'll decrease the concentration of one of the ions and shift it to the right. So Le Chatelier's principle. But we'll quantify the next one. We'll look at qualitatively and quantitatively as a separate video. Bada bing, bada boom, lunchtime.